Hi, in this video we're going to look at limits. Starting with the notation for a limit, the limit of f of x as x approaches a is the number L, is written as limit x approaches a of f of x equals L. So the limit is L, and the limit represents a y value that the function is getting closer to as x approaches a number. So let's look at a graphic example of a limit. Let's say here we wanted to estimate the limit as x approaches 1 of f of x from the graph. So by looking at the graph, you can see that f of x is this curve. Now your x values are here. As x approaches 1, that literally means x gets close to 1. So as x gets close to 1, so let's say the x value is here, that y value would be there, would be this number above 2. Similarly, if we look at a value to the right of the number 1, the y value would be just below 2. Now we want to know as x approaches 1, not equal to 1, but as it gets close to 1, notice that all of these x values that get close to 1 all make the y value get close to the number 2. Therefore, from this picture, we can say the limit as x approaches 1 of f of x is 2. We will look at more examples of limits graphically from both the left and the right side of the x value in some upcoming examples. There are also times that the limit may not exist. So one example of when a limit may not exist is in the case of the limit as x approaches 0 of 1 over x squared. The graph of 1 over x squared would be this right here. And if you notice as x approaches 0, 0 being right here as x is 0, the y values don't seem to meet at any point. Actually, as x approaches 0 from the left, the y value moves up toward positive infinity, and as x approaches 0 from the right side, the y values get close to positive infinity as well. So this would be an example of a limit that would not exist. What you see now in the PowerPoint slide that's also on this video are some properties of limits. So if you notice number 1, it says the limit as x approaches a of f of x is equal to the limit as x approaches a of c is equal to c, where c is a constant. So that means what if f of x is just a constant or just a number? So an example for number 1 would be like if f of x was equal to 4. And then let's say you want to find the limit as x approaches 1 of the number 4. Well, then the answer would just be 1, the constant. Very straightforward. So just make sure that you know that if the number of the function itself is just a number or just a constant, the limit as x approaches any number, you can put anything there, it's going to be equal to the constant itself. Let's look at property number 2. Property 2 says the limit as x approaches a of x to the n, so n being some positive integer, will be equal to a to the n. So if we look at an example for number 2, let's say f of x is equal to x to the third. And let's say the question says, find the limit as x approaches 1 of x to the third. So that just means, by the property, that means that a value gets plugged into where x is. So 1 to the third will be your answer, and you can simplify that to be the number 1. Now look at property number 3. Property 3 takes what we just saw in number 2, and now just says, okay, what if it was a sum and difference between the two functions? So we can take now another example. Let's say your function is x squared plus x to the 4th. And the question asks, find the limit as x approaches 1 of f of x. Well, that f of x is this function here. So really we want you to find the limit as x approaches 1 of x squared plus x to the 4th. And then all you need to do then is think of it as, if you see what the property says, it says the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x. So you can break it up. So we'll break this up into the limit as x approaches 1 of x squared plus the limit as x approaches 1 of x to the 4th. Notice I used the same sign that was placed in the original function. So if it was an addition, it's the plus sign. If it's subtraction, it's a minus sign. Now we use property 2, and we plug the 1 in, so you get 1 squared plus 1 to the 4th. And that's 1 plus 1, and that's the number 2. Now look at property 4. Property 4 is just like the others as well. So if you're taking the limit of a product, it's equal to the limit of each of the separate terms of the product. So let's look at another example. So let's say the limit as x approaches 2 of x squared times x to the 4th. Now yes, we can simplify that function itself here, but we're not. We're going to just work with it so we can use the property. So now, using the property, that means we can break this into the limit as x approaches 2 of x squared times the limit as x approaches 2 of x to the 4th. Then you use property 2, which says you place the 2 into where the x is, and then you can evaluate it. 2 squared is 4, and 2 to the 4th is 16, and then 4 times 16 is 64. And that will be your answer. Lastly is property 5, and that property says that if there's a constant in front of the function, well, you can just keep the constant out and then evaluate the function and then multiply them later. It's more straightforward than it looks in the property. So if we have a limit as x approaches 1 of 4x squared. So your constant here is 4, which is being multiplied toward the function x squared. So it's the coefficient. So when you plug the 1 into here, you're going to still use property 2. You're just going to keep that constant or that coefficient for after. So we can think of this as 4 times the limit as x approaches 1 of x squared, which is 4 times, when you plug the 1 in there, 1 squared, which is 4 times 1, which is 4. Normally, I don't go through the whole process of breaking this up. I really just look at the statement and I think of these properties intuitively. And I would say, can I plug the 1 in? Sure. This would be 4 times 1 squared, which would be 4. So as you become more comfortable with the properties, you don't have to itemize each and every piece of them. Now there are 2 more properties that we're going to look at. Property 6 and 7. Property 6 deals with quotients. Same idea as the product, just the only difference here is that you have to make sure that the limit of the denominator function isn't going to be 0, because then it will be undefined. And then example 7 deals with roots. So let's look at examples of both 6 and 7. So an example for number 6. So you had the limit as x approaches 1. And we can combine a few pieces here. Let's say we did 3x squared plus x all over x plus 1. So in essence here, we're going to combine properties 1, 2, 3, and 4, and 5 in this one example, and 6, because that's the one we're looking at. So we're going to look at the limit as x approaches 1 of the numerator all over the limit as x approaches 1 of the denominator. So we can plug in the x value into here by using the properties that we saw before. You can take the limit of a sum and take a limit of each of them separately, the limit of a coefficient with a function, and evaluate that, and the same thing with the denominator piece. So we can think of this as 3 times 1 squared plus 1 all over 1 plus 1, and that will give us 4 all over 2, which is 2. Now let's look at number 7, or property 7. Property 7 says the limit as x approaches a of some nth root of the function is the same thing as you taking the nth root of that limit of the function. So if we had the limit as x approaches 1 of the square root of x, that's the same thing as you taking the square root of the limit as x approaches 1 of x. So this portion here underneath the radical you can evaluate. It becomes the square root of 1, and the square root of 1 is plus or minus 1. Really, we don't ever write the square for the square root, so you don't see this. I just put it there so that you can see that it's like a property. Whatever root it is, that's the rules you use. The more practice you do, the more you'll see that these limits become more intuitive. You don't need to always think about which property number are you using. As you become more comfortable, you'll be more at ease to just go ahead and evaluating the limits.